In the very first video of this series, we have seen that linear models are all about solving approximate linear equations. In that video, we also saw an example, an artificial example of such an approximate linear equation. In this video, we shall take a look at a vast source of such approximate linear equations. Consider, for example, this particular spring system. So here is a spring and from which some weight is dangling. Now in this case, what we can do is that we can change this weight and accordingly this height will actually change. Say for example, if I change this height, change this weight, so if I make it heavier, in that case this changes. So this is an experiment that we have all carried out during our higher secondary days in laboratory. So here this was the input and this length was the output, and we are interested in measuring or interested in assessing the relationship between this input and this output. Now this particular example is a special case of a more general setup that we can represent as a black box. So here we are not interested in knowing how the spring works, only we are interested in understanding its input-output behavior and not why such a behavior takes place. So we can treat this as just a black box. So the spring is like a black box, well in this case it looks like a green box, but you understand. And the input is the weight and the output here is the length. And we put various inputs, so various values of the weight, and see what are the various values of the length that we see. Based on that, we want to make some inference about how this object behaves. Now this idea of treating something as a black box occurs in every walk of science, and the general setup is like this. You have some kind of a system and there are inputs, may not be one, here I am showing 4 inputs, and there may be outputs. In this case I am showing only one output, and that is the case that we will be always working with in this class, one output and one or more inputs, and this thing I have just called a system. Now there are various examples of this. Here for example is one of them. So it could be that this system is a patient. So this is a clinical example, and this patient has been given some medicine, a drug, that is one input. Now the patient has also some age which is not given to it, but the effect of the drug may very well depend on the age of the particular patient. So we have another input which is this age, and then the gender of the patient is also yet another input. So there are 3 inputs. Based on that, we have the output, which is some kind of a diagnostic measure. In this case, I have taken blood pressure, BP. So here the system is the patient, there are 3 inputs, and we are measuring the output. And we are trying to understand possibly what is the effect of the drug, whether the effect of the drug depends on age, depends on gender, and things like that. Yet another example of the same black box approach is maybe taken from the agricultural world. And here the system is a plot of land, and you are sowing some crop in it, paddy or wheat or whatever, and you are also applying some kind of a manure. It could be compost, it could be magnesium, phosphate, whatever, and you are and the response that you are measuring is the yield. So again you are treating this as a black box, and you are trying to understand how this particular plot behaves in terms of crop and manure, which manure is good, which is bad, or whether manure has an effect or not, or if some manure is good for some crop and some manure is bad for some crop, and you are assessing all these things by looking at the output, the yield. Now in all these cases, we cannot ignore the fact that there is going to be some amount of random error. Now what does that mean? This means the following. In this example, suppose we take two identical plots, as identical as possible. We sow the same crop in both the plots, apply the same manure, do everything similarly. Do we expect that we will get precisely the same yield in both cases? No. There will be some amount of variation, inevitable, because there are so many other things that we could not take into account. All those things put together, I have put it in this random error thing. So I cannot really say that this output is just a mathematical function of these inputs. So there is something which is still left out. So all those things are summed up here. Now I can say that this is actually a mathematical function of all these three inputs, including the random error. So typically when we will model this situation, I will assume that there is a precise mathematical relationship, possibly involving unknown parameters, that will determine this output from all these inputs. Mathematical, that is precisely mathematical. The randomness comes into picture because of one random input. This random input is what is causing the output to be random. So there is no randomness in the form of the entire thing. So let us consider this example once again, this black box example. So I have a system sitting here, and I have also some inputs and one output. You can hardly see it. Okay, you can now see it. One output. Now in this case, there are certain terms that we use often. One terminology is like this. So let's take this thing. So all these inputs may be either categorical, taking some only say some finitely many values, or they could be continuous. And this output will be calling it as response, and we have the random error. Now a categorical input, something like gender or age group or smoking habit, they are generally called factors. These are called factors. And if I consider a continuous input, that is generally called a covariate. There may be one or more covariate input, one or more factor input. So we have got factors, we have got covariates, and the response we will always assume to be continuous, and we will also assume that the random error is always continuous. Now it is possible to consider cases where the response or the random variable, these are also categorical, but we shall not discuss them in the first half of the course. So for a linear model, we will consider either categorical inputs, factors, or continuous inputs, or maybe both, but the output will always be continuous, and so will be the random error. If we allow the response also to be categorical, discrete, that will be what is called a generalized linear model. There are a few terminology that are generally used connected with the world of linear models, depending on how many factors you have and how many covariates you have. These are not terribly important things to know, but helps. For example, if in your black box setup you have only factors, then you call it an ANOVA model. ANOVA is an abbreviation for analysis of variance. We'll take a closer look at what is meant by analysis of variance, but for the time being, just remember that if I have a black box setup where I have only covariates, then, only factors, no covariates, that is only categorical inputs, then I will call that an ANOVA setup. For example, if I am working with a situation where I have, say, two drugs and gender, and my system is a patient, in that case, that will be called an ANOVA setup. I do not have any covariate. But if I have something like age, which is the continuous thing, then I will not call it ANOVA. Now on the other extreme, I have the situation where I have got, okay, so before that, let me just introduce one more term. If I have got k factors, then I will call it a k-way ANOVA. If the number of factors is k, no covariate, then I will call it k-way ANOVA. So if there is only one input and that is a categorical input, a factor input, that is one-way ANOVA. If there are two categorical inputs, two factors, then that will be called two-way ANOVA, and so on. Now if on the other hand I have the other extreme, I have only covariates. So I do not have any factor at all, just covariates. Then I will call it a regression set. Regression, the term regression is actually used in a far more general sense, even outside the scope of linear model. We might have nonlinear regression as well. But in the world of linear models, the term regression is generally reserved for the situation where we have only covariates. Now what happens if we have both covariates and factors? In that case, we call it an ANCOVA model. ANCOVA, analysis, AN stands for analysis of covariance. Analysis of covariance. So that is, in a sense, the most general thing. And every software has some kind of arrangement for analyzing ANCOVA, and then they specialize, they just drop the factor part to do regression, and then they drop the covariate part to do ANOVA. So ANCOVA is the most general thing. What we are going to learn is basically ANCOVA, and the same technique may be used for ANOVA as well as regression, to be precise, linear regression. Here also the same terminology of way works. If the number of factors is k, in that case we call it k-way ANOVA, k-way ANCOVA. Observe that the number of covariates plays no role in this terminology. These are just some names. You will often see them used, and you will often see that when you are trying to use a software other than R does not use these sort of terms much, but if you are using something like SPSS, etc., then you sometimes need to know this terminology. Okay, since today we are in a mood for learning various terms, let us learn a few more terms. These are important terms. Suppose we take this example where I have got the system is a patient and we have got number of inputs. I can see that I have got medicine here, then I have got gender, and then I have got blood pressure before the medication, and the output is the blood pressure after the medication. And we of course have random error. Now in this case you can see that these inputs, they are categorical, the factor, then factor, and then this one, blood pressure before, is a covariate. So we have already distinguished them according to whether they are categorical or continuous. But there is yet another way by which we can distinguish them. It is like this. Consider this input, which is the medicine. Now that input is something which the doctor, the experimenter, introduced in a voluntary, in a deliberate way. So you applied the medicine. And such a thing is called treatment. So by a treatment, the term itself comes from clinical studies. We mean something, some input, generally categorical, maybe a covariate thing, which is administered in a conscious way. So such a thing is called a treatment. On the other hand, gender, that is not administered in a conscious way, so that is called a control factor. That's kind of weird terminology, because the thing that you can control is called treatment, the thing you cannot control is called the control factor, but that's the term that has come to be stuck. So by control factor we mean something which is already there, you are not applying it, and it could be, so it need not always be a factor, it could also be a covariate, but generally the term control covariate is not used. For example, if you take this blood pressure. So that is also not administered by the doctor. So we generally reserve this term treatment and control for factors only, though the same concept will also work for covariates as well. We just do not use those terms generally. So the term treatment and control factor are reserved only for the categorical inputs. So these are the two terms that we should remember. Now, just as in case of factors and covariates, we have certain terms. So if we do not have factors, then we call this base. If we do not have covariates, we have a different name for that. Similarly, in this case, so if we have a situation where we have got at least one treatment, that is, there is at least one input which is consciously applied by the person who is carrying out the study, we call that a statistical experiment. Experiment, you understand, because you are consciously doing something to the system and looking at the output. Statistical, because we are taking random error into account. If on the other hand, you do not have any treatment, then all the inputs were already there, you are merely a passive observer, then you call it an observational study. In various social study scenarios, that is what happens. You are not changing anything. You are merely looking at the system as it is. You are merely taking some students, possibly from Bengali medium schools and English medium schools, and looking at their, say, final score in class 10 examination, and you are trying to assess whether medium has any effect on the score. That will be an observational study because you did not change the medium consciously. Every student came with his or her own medium of education, and then you merely observe the scores, which are the yield, which are the responses. So that will be an example of an observational study. So in this lecture we learned certain standard terminology. You will see them all over the place. So this will help you to read standard literature.